learners, welcome to Education Online program. I am teacher Willa Lucia. So in our previous lesson we learned a lot about mass and weight, starting from the definition of mass and weight, then going down to why some objects experience weightlessness. Then we went even to know more about the relationship between mass and weight. Then we also the differences. So in the differences between mass and weight, we got something there that mass is a scalar quantity and weight is a vector quantity. So that takes us to another subtopic for today, which is the scalar and vector quantities. So we have scalar and vector quantities. You'll see that in physics or in science, all measurements have been categorized. It is either in under scalar or the vector quantities. So that meaning that we have so many quantities, but we are going to specifically be looking at the scalar and the vector quantities. So if we look at that, so if we are saying that all measurements are categorized into these two things, what could be the definition of this, and how do you categorize a specific measurement under that, and why do you think that that measurement falls under scalar quantity or the vector quantity? Let's take a look at this. We have scalar quantity. How can we define scalar quantity? So with scalar quantity here, we are dealing with quantities that only have magnitude, or we can say the size. These quantities here do not have direction. You cannot say that they take a specific direction, because already putting it under scalar means that it does not have a specific direction it takes. So we have a scalar quantity is a quantity that has only magnitude or size without direction. So if we define it like that, what do you think are these quantities? What are these measurements that we can put under scalar quantity? So let's take a look at the examples. Examples of scalar quantities. There are so many measurements that you can put under that. So many measurements that have got only the size. They only have their magnitude without the direction. Let's take a look at time. As one of the examples of scalar quantities. When you look at time, you'll see that it is a measurement of maybe a week, maybe days, or you're talking about a year. So it doesn't have a specific direction it's going to take. If you say that I want to finish, maybe you're constructing and you want to finish that building in probably 1 year, you see there you do not take a specific direction to reach that 1 year, but it's just a total, it is just one thing that has only size. It is that size there, the length is what is known as the size, and it is that length there that qualifies it to be a scalar quantity. So we have another example, which is the volume. Does volume have any direction? For instance, if you get some water and pour in a bucket, do you say that this water has taken this direction here, or this water in the bucket is moving in this direction? No, because this volume here, it will just take the size of that water in the bucket. It measures only how much that media is present. If you talk about the volume, how much of that water is present in that basin. So it does not show you that there is a direction the water will take. That's why you find our volume as a scalar quantity. Let's look at another one. We have distance. Look at this example. You want to go to your grandmother's house. This is right here. This is your grandmother's house. So you want to move there, and you're right here. These are all, this is just an empty space that can take you there. You don't take a specific with this distance here. You'll see that there is a point. It is just this point, and where you're standing, this length here is what is known as the distance. So it doesn't mean that it has a specific direction you have to move. You can either start moving from here, you go like this, like this. It is not taking a specific direction, which maybe can be straight or circular in nature. You have to go like that. So you see, that is how the distance becomes a scalar quantity. So we have another, which is the energy. Let's look at this example here, energy. So look at yourself. If you have like something really heavy, maybe a chair, you want to lift the chair up, what are you going to use? You're using the energy, maybe to try just to swing it. You're trying to swing the chair. So you're using that energy in you to do that. Do you see a direction the energy takes to come out from you? The energy doesn't take any other specific direction. What it does, it is just the amount of that energy, the size, how much energy do you need to swing the chair around. That is why energy becomes a scalar quantity instead of the vector quantity. We have so many examples of this. We have the temperature. Temperature has a very unique quantity. Temperature can fall under scalar quantity, or it can fall under vector quantity. But then here, how does it become a scalar quantity? Here I've just written it as temperature. So that writing it alone like that confirmed it there, because here I am measuring to what degree is your temperature. Okay? So how is the temperature of a specific place? It's just like you're just coming to measure that temperature alone. Okay? But we are going to see how unique is temperature. How come that it's also a vector quantity? We shall see that when we reach the vector quantities. So we have so many of these, ranging to density. We can even have density also as another example of scalar quantity. There are so many of them. Let us look at this vector quantities. We have our vector quantities. Defining vector quantity just comes as the opposite of the scalar quantity. Because if you look at the definition of a scalar quantity, they are saying it's a quantity that has only magnitude. It doesn't have direction. That means that our vector quantity has got both direction and the magnitude. So it has the size and it has a specific direction it is taking. So we can define a vector quantity as vector quantity is a quantity that has both magnitude and direction. So for the vector quantities, that size of a media is accompanied by a direction it takes. So let's take a look at some examples of these vector quantities. So let's have our examples. Of vector quantities. Just like the scalar quantities, there are so many examples of these vector quantities. Let's take a look at some of the examples. We have force. One of it you can say is the force. We say that force acts in a specific direction. But then this force that is acting in a specific direction has a size. How much force do you apply for the force to move in that direction? Let's take a look at example of, pulling you have a cow, you want to pull it. So when you're pulling this cow, you have that amount of energy, that amount of force you need in order for the cow to change the position from where it is standing and follow you probably. So that force you're applying is the amount. It becomes it has the size because it needs, you measure it, how much more do you need to apply in order to pull the cow. So to what direction are you pulling the cow? So that direction means that that force you've applied has a specific direction that it is taking. So that is why our force becomes a vector quantity. So we have weight. Weight is also another example of this vector quantity. Because if you look at the definition of weight, we are saying that the weight is a force exerted on an object by gravitation, or by gravitational pull, or by gravity. So if it is a force, since we already know force has direction, that force there gives weight the direction it takes. So what of the size? How does it come about? We say that to get weight you have mass, and we know that mass is already a measurement of something, a size of something. So the mass in the weight gives it that magnitude aspect, and the force in the weight gives it its direction. So that's why our weight is an example of a vector quantity. let's look at acceleration. Acceleration has a magnitude and also the direction. If you're trying to accelerate your car, you're trying to move your car, okay? So that car is taking a specific direction. So with that acceleration there, it has the size, because it depends on how much you need to apply in order for this car to move. How much do you have to accelerate it to allow it to allow the motion, the movement of the car? So we have also what is known as we can have our velocity as another example of this vector quantities. There are so many. These are not the only examples. We have things like displacement, we have things like momentum, we have so many of these. So let's look at this temperature, because we said temperature is a scalar quantity, and to some other extent it also becomes a vector quantity. How is that? For it to become a vector quantity, you don't just state it as temperature. We say the increase or decrease in temperature. Let us look at this increase or decrease in temperature. So this increase or decrease of temperature gives it the direction it takes. For instance, if you take my temperature, okay, if you want to see my temperature, so checking it, let me say we are using a thermometer. So you look at the alcohol or the okay, let me just, we are using, assuming we are using the thermometer that has the alcohol as the liquid inside. What happens is that you'll see this alcohol rising in the thermometer, in the tube. We have it. Let's take a look at our thermometer, just like this. We assume this is how our thermometer looks like. Okay, the diagram is a bit horrible. So this is a thermometer here. We are going to use this thermometer to determine the temperature of my body, and the thermometer has the tube inside here containing the liquid right there, and then it has the scales, graduated scales there. So we are using our thermometer here to determine my temperature. At first, if you see that the alcohol, the liquid here, is only at this bulb. So what happens is that the moment you put it on my body or under my armpit to determine my temperature, you'll see that this alcohol will try to move upwards. You'll see it moving in this space here, meaning that there is an increase in the temperature of my body. So this movement here shows the direction of the temperature. So you can say it is moving from the bulb up to this other scale here. So the decrease also gives it the direction. Imagine now, after pulling it out, you've checked my temperature, you've removed, it's no longer on my body. It's now in another, recording a different temperature, maybe just any other room temperature. You'll see that the moment you remove the thermometer, there is going to be a fall. There will be a fall in this. The liquid that at first moved up here is going to be falling down, reducing, coming back to the bulb. That means that at first you took an upward direction. So when you removed it from my body, it is in another place. There will be a fall. It is taking another downward direction. So there is a magnitude of that, how much temperature you've recorded, to what degree Celsius did you record the temperature. You see that? So to what degree of the temperature gives you the size, the magnitude of this temperature. So the rise and the fall, the increase or the decrease, gives you the direction to which the temperature had taken. So that is why you see that our temperature can be either a scalar or a vector quantity. So now, since we've known we have seen so many examples, let's look at the relationship between a vector and a scalar quantity. Let us have it here. What do you think is similar between these two? Let's have it here as relationship. Relationship between scalar and vector quantities. What is that thing that makes this vector and scalar quantity be similar? Because if you're talking about the relationship, we are talking about the similarities between the two quantities. So we can see that from our definition of scalar and vector quantity, there is this term, the magnitude, or the size. That means that the similarity between a scalar and a vector quantity can come from the definition, meaning that they both have the magnitude or the size. We can say both have magnitude and size. Not in size, but we can say or size, because size is another term of magnitude. So what other thing do we have? Both are used to denote physical quantities. Because if you look at the mass, if you look at the displacement, those are the physical quantities. So we are just using these two to denote them. So meaning that the similarity again comes here as both are used to denote physical quantities. So if we say that, if we have like that, because we know that these ones here, the scalar and vector quantity, all these other physical quantities fall under these two. So they are the major, they are the umbrella of these other physical quantities. We still have another one. They both have units. Both have units. How do they have the unit? Look at the example of vector quantity. We have force. Force is having its SI unit, which is the Newton. So if you come back here and look at time, which was under a scalar quantity example of that, what happens is that time has a specific unit. So what is the unit of time? It is seconds. So you see that all these other examples we listed under scalar have got units. Even all these ones have got units. Weight is measured either in grams or kilogram. So those are the similarities that the scalar and the vector quantities do have. Also, we say that they have specific dimension. So both of them have specific dimensions. So let's have those as our Similarities. There are more other similarities you can also find. Let's look at now the differences. If these three things here we've noted are the things connecting these two, the scalar and the vector, what do you think are the other things that can differentiate the two? Let's look at that. So we can have it as the differences between scalar and vector quantities. So what are those things that distinguish the two? If we have these other things as those things that connect them, what are those? So we can still have from our definition. You see that let us have it in form of a table so that we don't get confused that much, like that. Where we're going to have our scalar quantities, and then here we shall be noting the differences under vector quantities. One of the difference comes direct from the definition of the two. We said one has the magnitude only and the other one has magnitude and direction. So we have the scalar. The difference here is it has the only magnitude. It has only magnitude. But the vector quantities have got both the size and also the direction they take. So we can say that have both direction and magnitude. That means that the size of that quantity has got its direction it takes. It can either move upwards or downwards. We can say that scalar quantities, they only change when there is a change in the magnitude. So they change in magnitude, or you can say in size, which is not the case with the vector quantities. You find out that with the vector quantities, it will change when there is a change in either the magnitude or the change in the direction, or the change in both the magnitude and the direction. All of that can also give the change to that measurement there. So this one has it changes with change in either direction, size or direction, or even both. So they can change at the same time, or one can be the one changing, so giving the rise to the change in that quantity. So we also still have others like the scalar quantity here cannot be resolved. It cannot be resolved because it doesn't matter to what direction you take it, it still remains the same. That means the size of that media does not change. But with a vector quantity, it can be resolved because it has a specific direction. So you can easily resolve that. So there are so many differences between this scalar and the vector quantities. But for today, we shall stop with these other differences. So we've learned so many about the definitions. I hope now you can define a scalar and a vector quantity. You can differentiate between the two, and you can still get the similarities between the two quantities. Thank you very much for attending with me. We shall meet again in the next lesson.